Welcome. In this video, we are doing a complete walkthrough of Git, the most widely used version control system in the world. Whether you are an absolute beginner or someone who just uses git add and git commit and nothing else, by the end of this video you will understand Git deeply, from how it stores data internally to advanced workflows used in real professional teams. Let's get into it. So what is Git? Git is a distributed version control system, or DVCS. Its job is to track changes in your source code over time. Think of it as an incredibly powerful undo history for your entire project, one that lets multiple developers work simultaneously, branch off in different directions, and then bring their work back together safely. Click. Why has Git become the industry standard? A few reasons. Speed. Nearly every operation in Git, committing, branching, merging, happens locally on your machine. There is no round trip to a server. It is fast. Integrity. Every single object Git stores is identified by a SHA-1 hash of its contents. If even one byte changes, the hash changes. You cannot accidentally corrupt history without Git knowing about it. Nonlinear development. Branching in Git is so lightweight and fast that you can create a new branch, experiment, throw it away, and start a new one in seconds. This encourages a style of development that would be painfully slow in older systems. Distributed. Every developer who clones a repository has the full history. Every clone is a complete backup. Look at the timeline on the right. Git was born in 2005 when Linus Torvalds, the creator of the Linux kernel, needed a replacement for the version control tool the kernel team had been using. He wrote the first version of Git himself in about 2 weeks. 3 years later, GitHub launched, and the rest is history. Today there are over 100 million repositories on GitHub alone. Before we go deeper, it is worth understanding why distributed systems like Git exist by contrasting them with the older centralized model. In a centralized system, like Subversion or SVN, there is a single central server that holds the entire history. Every developer has only a working copy of the files, not the full history. To commit, you must have a network connection to that central server. The problem should be obvious. The server is a single point of failure. If it goes down, nobody can commit. If it is destroyed without a backup, you lose everything. And you cannot work offline. Every meaningful operation requires the network. Now look at Git's model. There is still a central remote, typically GitHub or GitLab, but it is just a convenience for sharing, not a requirement for working. Every developer clones the repository and gets the full history on their own machine. They can commit, branch, merge, and explore history entirely offline. The benefits follow naturally. Full local history, offline commits, multiple backups by default. Every developer's clone is one. This distinction is the foundation of everything Git does. Next, this is probably the single most important mental model in Git. The 3 trees or 3 areas that Git uses to manage your project. Let's walk through the diagram from left to right. The working directory is just your file system, the files you see and edit in your code editor. When you modify a file, it lives here in a modified state. Git knows it is different, but has not recorded that change anywhere yet. The staging area, also called the index, is Git's drafting table. When you run git add, you are copying a snapshot of a file's current state into the staging area. This is the set of changes that will go into your next commit. Crucially, you can stage some files but not others. This lets you craft very precise, focused commits, even when you have changed many files at once. The local repository is where commits live permanently. When you run git commit, Git takes everything in the staging area and writes it as a new immutable snapshot into the .git folder on your machine. This is your full local history. The remote repository, on GitHub, GitLab, or wherever, is a copy of your local repository that you share with your team. Git push sends your commits there. Git fetch and Git pull bring their commits down. The table at the bottom maps each area to its actual storage location. The staging area is a file called .git/index. The repository is the objects inside .git/objects. Understanding these 3 areas makes almost every Git command make intuitive sense, including all the ways to undo things, which we will cover later. Let's go one level deeper and look at how Git actually stores data internally. This is where Git becomes really elegant. Git stores everything as one of 4 object types, and every object is identified by the SHA-1 hash of its contents. Blobs store raw file contents, not the file name, just the bytes. The text of your Python file, for example. Trees store directory listings. A tree maps file names to blob hashes for files, or other tree hashes for subdirectories. Think of it as a directory snapshot. Commits are the objects you create with git commit. A commit stores a pointer to a tree, the root of your project at that moment, a pointer to its parent commit or commits, and metadata, author, date, and message. Tags are named pointers to specific commits. Annotated tags store extra metadata, like a message, and a tagger. Follow the diagram. A tag points to a commit. The commit points to a tree. The tree points to two blobs, the readme and main.py, and to a subtree for the src directory, which in turn points to another blob. Click the important insight here, is in the callout on the right. Git is essentially a content addressable file system. Because the hash is derived from the content, identical files across different commits share the same blob object. Git deduplicates automatically. If you rename a file without changing it, Git does not store it twice. Next. Now let's talk about how commits connect over time, and what head means. Click every commit in Git points to its parent, so your history forms a linked list of snapshots, from the very first commit to the most recent. The top diagram shows 4 commits: init, add readme, add main.py, and fixbug, arranged as a Git graph. Click the second diagram shows the same history as explicit objects. Each commit box contains a short hash and a message. Each one has an arrow pointing back to its parent. You can see 2 pointers at the end. Main and head both point to the latest commit, J1K2L3. Click. So what exactly is head? Head is a special pointer that tells Git, this is where you are right now. It almost always points to a branch name, like main, rather than directly to a commit. When you make a new commit, the branch pointer moves forward, and head moves with it. When head points directly to a commit hash instead of a branch, Git calls that a detached head state. You can look around in that state, but any commits you make there will be orphaned, unless you create a branch. Click the commands on the right. Git log, one line, graph all, give you a visual representation of your entire history in the terminal. And cat.git/head reveals exactly what head is pointing to right now. Next, let's go through the core Git commands you will use every single day. Setup. Things you do once when you first configure Git on a machine. Git config, -global user.name and user.email set your identity, which gets baked into every commit you make. Setting core.editor to code wait makes VS Code your commit message editor. Very handy. Git init creates a brand new repository in the current directory. It creates the .git folder and nothing else. Your first commit sets everything in motion. Git clone copies an existing remote repository to your machine, full history included. The second form lets you specify the local folder name instead of using the repo name. Staging and committing, the commands you run most often. Git status is your best friend. Always run it before adding or committing. It shows you exactly which files are modified, which are staged, and which are untracked. Git add file.py stages a specific file. Git add stages everything. Git add vadman.p is the power user option. It walks you through each changed hunk interactively, so you can choose exactly what goes into the commit. Git commit-m with a message creates the commit. Git commit amend rewrites the last commit, but only use this before you push. Once commits are shared, amending rewrites history. Git diff shows unstaged changes. Git diff staged shows what is in the staging area versus the last commit. Always do git diff staged before committing so you know exactly what you are recording. Next, branching is where Git really shines, and it is important to understand what a branch actually is under the hood. A branch in Git is not a copy of your code. It is simply a lightweight movable pointer, a text file containing a single commit hash. That is really all it is. This is why creating a branch in Git is essentially instant and costs almost no memory, regardless of your project size. Look at the diagram. From commit G7H8I9, add main.py, the history diverges. The main branch keeps going straight to fix bug. Meanwhile, feature/login branched off at the same point and has 2 more commits, new feature, and more work. Head is currently pointing to feature/login, meaning we are working on that branch right now. On the right, you have the branch management commands. Click git switch native c feature/login is the modern way to create and switch to a new branch in one step. The older syntax was git checkout-b. You will see both in the wild. Git branch a lists all branches including remote tracking ones. Git branch-d deletes a branch safely. Git will refuse if the branch has unmerged changes. Git branch-d forces the deletion. Be careful with that. One thing that trips people up, deleting a branch just deletes the pointer. The commits still exist in the object store, for a while at least. Git's garbage collector eventually cleans up unreachable objects. Now let's talk about bringing separate lines of work back together. Merging. There are 2 main types of merge, and the first one is beautifully simple, the fast-forward merge. Fast-forward happens when the branch you are merging in is ahead of the branch you are merging into, with no divergence. Look at the before diagram. Main points to C2, and feature points to C3, which is directly ahead of C2. There is a straight line from main to feature. In this case, merging is trivial. Git does not need to reconcile any differences. It simply moves the main pointer forward to C3. No new commit is created. No conflicts are possible. The after diagram confirms it. Main now points to C3, and the feature pointer is gone after the merge. Fast-forward merges give you a clean, linear history. If you want to prevent them and always create a merge commit, even when fast forward is possible, you use the NoFF flag, which we will see on the next slide. Next, things get more interesting when both branches have diverged, when main has new commits that feature does not have, and feature has commits that main does not have. This is the three-way merge. Look at the Git graph. C1 and C2 are the shared base. Then feature adds C3 and C4. Meanwhile, main adds C5. The two branches have diverged. To merge them, Git performs a three-way merge. It looks at the common ancestor C2, the tip of main C5, and the tip of feature C4, and creates a brand new merge commit M1 that has two parents, C5 and C4. The merge commit M1 represents the reconciliation of both lines of work. Click the commands on the right, cover the important variations. Git merge, NoFF feature/login, forces a merge commit even when fast forward would be possible. Useful when you want the history to clearly show that a feature branch existed and was merged. Git merge, squash takes all the commits on the feature branch and folds them into a single stage change, which you then commit yourself. This gives you a very tidy history, but loses the individual commit messages from the feature branch. And Git merge, abort is your escape hatch if a merge goes wrong. It rolls everything back to where you were before running merge. Next, merge conflicts are one of the things that intimidates new Git users the most. Let's demystify them. A conflict occurs when both branches have modified the exact same lines in the same file in different ways. Git cannot decide which version to keep. It needs you to decide. Click the flowchart on the left shows the process. You run git merge feature. Git checks whether there are any conflicting changes. If there aren't, it creates the merge commit automatically and you are done. But if there are conflicts, Git halts the merge and writes conflict markers directly into your files. Click those markers look like the code block on the right. Everything between less than, then hid, and equals is your version, what exists on your current branch. Everything between equals, and greater than feature/login is their version, what came in from the feature branch. Your job is to edit the file to resolve the conflict. Delete the markers, decide what the final version should look like, maybe a blend of both, save it, and then stage it. Click after manually editing. Git add the resolved file, then git commit to complete the merge. Git will open your editor with a pre-filled merge commit message. Git merge tool launches a 3-panel visual diff tool if you prefer a GUI approach. And git diff filter equals U, shows only the files with unresolved conflicts, very useful when many files conflict at once. Conflicts are totally normal in collaborative development. Do not fear them. They are just a flag that says, a human needs to make a decision here. Rebase is one of the most powerful and most misunderstood features in Git. Let's break it down carefully. Rebase takes a series of commits and replays them onto a different base commit, creating a linear history, as if the feature branch was always branched from the latest version of main. Look at the before diagram. C1 and C2 are shared. Then main adds C3. And feature branched off C2 and added C4 and C5. Now you run git rebase main from the feature branch. Look at the after diagram. Git detaches C4 and C5, moves the base to C3, which is the tip of main, and reapplies C4 and C5 on top, creating new commits, C4' and C5'. They contain the same changes as before, but they are technically new commits with new hashes, because their parent is now C3 instead of C2. The result: a perfectly linear history that reads as though the feature was always built on top of the latest main. Click the commands, git switch feature/login, then git rebase main. If there are conflicts during replay, Git pauses, you resolve them. Run git add, then git rebase, continue. If you want out entirely, git rebase, abort restores everything to where it was. Interactive rebase with iHead, approximately 3, opens an editor where you can reorder, squash, or drop the last 3 commits. We have a dedicated slide for that later. Click now, the golden rule of rebasing, and please burn this into your memory. Never rebase commits that have already been pushed to a shared remote branch. Rebase creates new commits with new hashes. If teammates have built work on top of your original commits, and you rebase and push with force, you will rewrite shared history and cause chaos for everyone working on that branch. Rebase on local feature branches before opening a pull request. Great. Rebase on shared branches that teammates depend on. Never. Next. When should you use merge, and when should you use rebase? This comparison table settles the debate. History. Merge preserves the full, honest history of when branches were created and merged. Rebase rewrites it to be linear. Merge commit. A 3-way merge always produces a merge commit. Rebase does not. Conflict resolution. With merge, you resolve all conflicts at once in the merge commit. With rebase, you may resolve conflicts for each commit that gets replayed, potentially multiple rounds, though typically minor ones. Safety on shared branches. Merge is always safe. Rebase rewrites history, never safe on shared branches. Readability. This is subjective. Some teams find a flat linear rebase history easier to follow. Others find that merge commits provide valuable context about feature groupings. Click the Git graph shows what a merge-heavy history looks like. The diamond-shaped merge commits that some teams find messy. Click the recommended strategy that many teams use. Rebase locally to clean up your feature branch before submitting a pull request. Squash your WIP commits into logical units. Make sure the branch is up to date with main. Then merge into main with no FF to preserve the record that a feature branch existed. Best of both worlds. Next. Up to now, we have been talking about everything happening locally. Let's bring in remote repositories, the how of sharing work with a team. Click the sequence diagram tells the story clearly. Git push origin main sends your local commits up to the remote. The remote is updated. Git fetch origin is the safe option. It downloads any new commits from the remote and updates the remote tracking branches like origin/main on your machine, but it does not touch your local working branch. You get to look at what changed before deciding to integrate it. Git pull origin main is fetch plus merge in one step. Convenient, but it immediately integrates the remote changes into your local branch, which can create unexpected merge commits if your local branch has diverged. Git push-u origin features/login pushes a new local branch to the remote and sets up the tracking relationship. The U flag means subsequent git push, and git pull commands on that branch will automatically know which remote branch to talk to. Click a commands on the right cover git remote add origin, which is how you connect a local repo to a remote for the first time. Git push. Force with lease is the safer version of force push. It checks that no one else has pushed to the remote branch since your last fetch. If they have, it refuses the push, protecting teammates from having their work overwritten. Next. This one slide is worth pausing on, because the distinction between fetch and pull trips up a lot of developers. Look at the three nodes. The remote has commits A, B, C, D, and your local copy doesn't have D yet. Git fetch origin downloads the new commits and updates the remote tracking branch origin/main on your machine. Your actual local main branch is untouched. The purple tracking branch now knows about D, but your green local main still only has A to C. Now you can inspect what changed with git log origin/main, run your tests against it, or review the diff, all without affecting your working state. Then you decide to integrate it. Git merge origin/main or git rebase origin/main updates your local main. Git pull just does both of those steps automatically, fetch, then merge. Click the golden rule at the bottom. Prefer git fetch plus inspect plus git merge over a blind git pull on important branches. It gives you a chance to review what you are pulling in before it affects your working state. Now that we understand the core mechanics, let's talk about how teams organize their work using Git, starting with the feature branch workflow, which is the most widely used approach in the industry. Click the Git graph shows the pattern. You have a main branch. Every piece of work, a feature, a bug fix, a refactor, happens on a dedicated branch, isolated from main. Two features are being built simultaneously, feature/login and feature/dashboard. They run in parallel without interfering with each other. When they are ready, they get merged back into main. Click the 4 rules at the bottom, define the discipline that makes this work. Rule 1. Main is always deployable. Any commit on main should represent code that could, in principle, be shipped to production right now. This is a contractual guarantee the team makes to itself. Rule 2. All work happens on feature branches. You never commit directly to main. Rule 3. Branches are merged via pull requests or merge requests in GitLab terminology. This is the formal mechanism for proposing that a branch be merged, and it triggers code review, automated tests, and discussion. Rule 4. Code is reviewed before it merges. At least one other developer looks at the changes, ensuring knowledge sharing and catching bugs before they get into main. This workflow scales beautifully, from 2 developers to 200. For teams that ship versioned releases, rather than continuous deployments, GitFlow offers a more structured workflow with dedicated branch roles for every phase of the release cycle. Follow the Git graph carefully. Main only ever receives code that is ready to ship, and every merge into main gets a version tag. Develop is the integration branch, where features are merged and tested together before they are put into a release. Feature/asterisk branches are cut from develop, worked on, and merged back into develop. When develop is ready to release, you cut a release/asterisk branch. On that branch you do final preparations. Bump the version number, write release notes, fix last-minute bugs. Then it merges into both main, to ship it, and back into develop, so develop stays in sync. And then there's hotfix/asterisk branches, cut directly from main for emergency production fixes. A critical bug is fixed, merged into main with a patch version tag, and then immediately merged back into develop so the fix is not lost. The table at the bottom summarizes the role of each branch type. GitFlow can feel heavyweight for smaller teams or projects that deploy continuously. The feature branch workflow or trunk-based development might be a better fit in those cases. But for projects with scheduled releases, Git flow provides a very clear, predictable structure. Next, one of Git's superpowers is the ability to undo almost anything. But there are multiple ways to undo things, and picking the right one matters a lot. Click the flowchart on screen as your decision tree. Let's walk through the branches. If you staged a file by mistake, git restore stagedfile.py. This removes the file from the staging area, but leaves your edits intact in the working directory. If you want to throw away edits in your working directory, git restore file.py. This is destructive. Your changes are gone. It is colored green on the flowchart because it is safe in the sense that you haven't lost any committed work, only uncommitted edits. If you want to undo the last commit, but keep your changes staged, git reset softhead approximately 1. Your changes are back in the staging area, ready to be recommitted differently. If you want to undo the last commit and unstage the changes, git reset mixed head approximately 1. This is the default mode. Your changes are back in the working directory, unstaged. If you want to undo the last commit and destroy the changes entirely, git reset hardhead approximately 1. That is shown in red because this is genuinely destructive. Changes are gone from working directory, staging area, and the commit itself. If you want to undo a pushed commit safely, git revert head. This creates a new commit that is the inverse of the target commit. History is preserved. This is the safe option for shared branches. And if you accidentally destroyed something and need it back, git reflog. We have a dedicated slide for that shortly. Next, let's solidify the 3 modes of git reset with a precise diagram. We have 3 commits, C1, C2, and C3, which is the current head. We run git reset head -1, meaning move back 1 commit. What happens depends on the flag. Soft. Git moves the repository back to C2, meaning C3 is no longer the head commit, but it moves C3's changes into the staging area. Your working directory still shows C3's state. It is as though you ran git commit, but then uncommitted it. Your changes are safe and staged. Mixed. The default. Git moves the repo back to C2, clears the staging area to match C2's state, but leaves C3's changes in your working directory as unsaved, unstaged modifications. Your work is safe, but you need to restage it. Hard. Git moves the repo back to C2, resets the staging area to C2, and resets the working directory to C2. All changes from C3 are gone. This is the nuclear option, shown in red for a reason. Click the callout at the bottom is critical. When you need to undo a commit that has already been pushed to a shared branch, use git revert instead. It adds a new commit that reverses the changes. History stays intact. No one's work is disrupted. Here's a scenario you will encounter constantly. You are halfway through a feature, your working directory is messy, and then someone reports an urgent production bug that you need to fix right now. You are not ready to commit your half-done feature. What do? The answer is git stash. Click the sequence diagram tells the story. Your working directory has half-done feature work. You run git stash push mam wip login. Git takes all your staged and unstaged track changes and pushes them onto a stash stack, a last-in first-out stack of saved work states. Your working directory is now clean. Your staging area is empty. You are free to switch branches, fix the bug, commit the fix, and come back. When you are ready to resume, git stash pop restores the top entry from the stack back into your working directory and removes it from the stack. Click the commands on the right cover all the variations. Git stash push -u includes untracked files, new files that you have not yet added with git add. Git stash list shows all your saved stashes. The notation is stash at 0 for the most recent, stash at 1 for the one before it, and so on. Git stash apply restores a stash without removing it from the stack. Useful if you want to apply the same stash to multiple branches. Git stash pop stash at 1 applies and removes a specific stash entry, not just the most recent. Think of the stash as a temporary clipboard for your work in progress. Next. Tags are named permanent pointers to specific commits. Unlike branch pointers, which move forward with every new commit, a tag stays fixed forever on the commit it was created for. Tags are the standard way to mark release versions. Click the Git graph shows it perfectly. Version 1.0.0 is pinned to the first commit, v1.1.0 to a later commit, version 2.0.0 to the latest one. These tags never move. Click there are 2 types of tags. A lightweight tag is just a pointer, like a branch that never moves, created with git tag version 1.0. An annotated tag is a full Git object that stores a message, the tagger's identity, and a timestamp. It is created with git tag, a version 1.0 m release 1.0, and is what you should use for release versions. You can tag any commit, not just head. Pass the commit hash as a final argument. An important gotcha: git push does not push tags by default. You have to explicitly push them, either one at a time with git push origin version 1.0, or all at once with git push origin tags. Make sure you push your tags before announcing a release. Next, Git log is one of the most versatile commands in Git. Most people only ever use the bare git log, but the filtering options make it a powerful investigation tool. Git log. One line gives a compact one line per commit summary, the short hash, and the commit message. This is what you will use most often for a quick glance at history. Git log. One line, graph all. Decorate is the power user alias. The graph flag draws a text-based branch graph in your terminal. All shows all branches, not just the current one. Decorate shows branch and tag names. The author filter shows only commits by a specific developer. Since, and, until filter by date range. grep filters by commit message content. Great for finding all commits related to a particular feature. Gitlog-P shows the full diff of every commit, what lines were added and removed. Useful for auditing a specific file's history. Gitlog follow tracks a file even if it was renamed. Gitlog-S deflogin is the pickaxe search. It finds commits where the string deflogin was added or removed. This is incredibly useful for tracking down when a function was introduced or deleted. Click and git blame at the bottom is for answering the question, who wrote this specific line of code and when? It annotates every line of a file with the commit hash, author, and date that last modified it. The -L flag limits it to a line range. The reflog might be the most underappreciated feature in Git. It is your ultimate safety net. The reflog is a log that records every movement of head, every commit, every branch switch, every rebase step, every reset. It is local to your machine and is not shared with remotes, but it is always there. Look at the diagram. The reflog output shows a reverse chronological list of head positions. Head at 0 is the most recent position, a reset that moved head back. Head at 1 was the commit before that. You can see a login feature commit and a fix. The middle box shows the disaster scenario. You ran git reset, hard accidentally, and the commit with your login feature, #9c1234, is no longer reachable through gitlog. It looks gone, but in the bottom box we save it. The #9c1234 is right there in the reflog. You can git checkout a 9c1234 to inspect the lost commit, then git switch-c recovery to create a branch from it, or git reset, hard a 9c1234 to fully restore to that state. Click one caveat. Reflog entries expire. By default, they are kept for 90 days. After that, orphaned commits can be garbage collected. So if you need to recover something, do it promptly. The reflog is the reason developers say, in Git, almost nothing is ever truly lost. Keep that in your back pocket. Git cherrypick lets you take a specific commit from one branch and apply it to another, without merging the whole branch. Think of it as selectively copying individual commits. The classic use case. A developer fixes a critical bug on the feature branch, and you need that fix on main immediately, without waiting for the entire feature to be ready to merge. Look at the before diagram. C5 on the feature branch is the hotfix commit you need. On main, the history only goes up to C3. After running git cherrypick C5 from main, Git replays the changes introduced by C5 onto main, creating a new commit C5'. It has the same diff as C5 but a different parent, and thus a different hash. Click the commands. Git cherrypick A1B2 C3D applies a single commit by hash. You can cherrypick a range with git cherrypick C1 C5 that applies all commits from C1 exclusive to C5 inclusive. No commit applies the changes without creating a commit, leaving them staged for you to review and commit yourself. Use cherrypick sparingly. If you cherrypick a lot of commits from one branch into another, that is usually a sign you should reconsider your branching structure. Next, not every file in your project should be tracked by Git. Build artifacts, compiled bytecode, virtual environments, editor configuration, log files, and most importantly, secret credentials should never enter version control. The .gitignore file tells Git which files and directories to silently ignore. Any file matching a pattern in .gitignore will not appear in Git status and cannot be inadvertently staged. The code block shows a .gitignore for a typical Python project. __pycache __/ and asterisk. py, Python's compiled bytecode files. These are generated automatically and should never be committed. .venv/env/env/ virtual environment directories. These contain hundreds of megabytes of installed packages that are fully reproducible from requirements.txt or pyproject.toml. .env and .env, environment variable files. This is the most important one. Database passwords, API keys, secret tokens, these must never be committed. If they end up on GitHub, even briefly, treat them as compromised. .idea/n.vscode/IDE configuration. Some prefer committing .vscode/ with shared settings, but generally it's better to ignore editor-specific files. Click. The pattern syntax on the right covers the essentials. Important .log with a bang is an unignore, it overrides a preceding pattern. Nibs-wool logs matches a log/directory anywhere in the tree. If you accidentally committed a file you meant to ignore, git rm cached file name removes it from the repository index without deleting it from your file system. Then add it to .gitignore and commit. Next. Interactive rebase is where you get to clean up your commit history before sharing it. This is one of the most practical skills in everyday Git use. Running git rebase, I had approximately 4, opens an editor with the last 4 commits listed, oldest at the top, 1 line per commit. Click each line starts with a command keyword, followed by the hash and message. By default, every line says pick, meaning keep this commit as is. The commands you can use, pick, leaves the commit unchanged. Reword lets you edit the commit message without changing the code. Edit pauses the rebase of that commit, so you can amend it with git commit, amend. Squash merges this commit into the previous one, and combines their messages. You get to write a new combined message. Fixup is like squash, but silently discards this commit's message. Drop removes the commit entirely. Click. The common pattern at the bottom shows what this looks like in practice. You have been working on a feature, and your raw commit history is messy. A few WIP commits, a typo fix, some fixed typo commits. Before opening a pull request, you run interactive rebase and squash the WIP commit into the main feature commit and fix up the typo fix, since it is just noise. The reviewers see only 2 clean, logical commits. Interactive rebase is the difference between a history that tells a clear story and one that reads like a debugging session transcript. Here is a scenario. You have a bug in the codebase, you do not know when it was introduced, and the project has hundreds of commits. How do you find the exact commit that broke things? The naive approach, check out commits one by one until you find the culprit, is ON. With 100 commits, that could mean 100 manual tests. Git bisect uses binary search to find the bad commit in O log n steps. With 100 commits, you need only 7 tests. With 1,000, only 10. Click the diagram illustrates. Your history goes from C1, known good, to C5, known bad. Git picks the middle commits, C3. You test. It is good. Now Git knows the bug is between C3 and C5. It picks C4. You test. It is bad. The bug is between C3 and C4. Since there is nothing between them, C4 is the culprit. Done in 2 tests. Click the commands. Git bisect start initializes the session. Git bisect bad marks the current commit as broken. Git bisect good, version 1.0, marks a known good tag or hash. Git now checks out the midpoint commit. You test manually, then tell Git the result with git bisect good or git bisect bad. Repeat until Git reports the exact commit. The real power move is git bisect run. Pass it a test script that exits 0 for good and non-zero for bad, and Git will run the entire bisect fully automatically without you having to do anything. Git bisect reset returns you to your original branch when done. 2 more advanced features worth knowing: submodules and worktrees. Submodules let you embed one Git repository inside another. This is common when a project depends on a shared library that lives in its own repository. Instead of copying the library files, you add it as a submodule, a reference to a specific commit in the external repo. Git submodule add pins the external repo at a path in your project. When someone clones your repository, they also need to initialize and update the submodules, that is, the git clone, recurse submodules flag, or the git submodule update, init, recursive command after a plain clone. Updating a submodule means going into its directory, pulling the new version, then coming back up to your project and committing the updated reference. Submodules are powerful but add coordination overhead. Weigh them against alternatives like package managers. Worktrees solve a different problem. By default, you can only have one branch checked out per clone. Worktrees let you check out multiple branches simultaneously in separate directories, all sharing the same .git folder. The use case: you are deep in a feature branch and an urgent hotfix needs attention. Instead of stashing, switching, fixing, committing, and switching back, git worktree add /hotfix. Hotfix/bug123 creates a second working directory with that branch checked out. You fix and commit there, then come back to your feature work undisturbed. Next. By default, Git trusts you when you set user.name and user.email. There is nothing stopping someone from setting user.email to your email address and making commits that appear to be from you. In open source projects and security-sensitive environments, this matters. GPG signing solves this. You create a public-private key pair. Your private key never leaves your machine. When you sign a commit, Git attaches a cryptographic signature using your private key. Anyone with your public key, which you upload to GitHub, can verify that the commit genuinely came from you. Platforms like GitHub show a green verified badge on signed commits. The commands walk through the full setup: generating a key with GPG, full generate key, telling Git which key to use with user.signing key, and enabling automatic signing with commit GPG sign true. After that, every commit you push will be signed automatically. Click the flow diagram summarizes it. You sign with your private key, push to GitHub, GitHub verifies against your public key, and the verified badge appears. A tampered commit, one where the content doesn't match the signature, will show as unverified. For most day-to-day work on private projects, signed commits are optional. But for any work where identity and integrity matter, they are worth the 5 minutes of setup. We have all worked in codebases where the commit history reads like fix, fix2, finally works, ASDF. That history is useless for understanding what changed or why. Conventional commits is a lightweight specification for writing structured commit messages that both humans and tools can parse. Click. The format is simple. A type, an optional scope in parentheses, and a short description. For example, feat, auth, add OAuth 2 login support. Click. The type conveys the nature of the change. Feat is a new feature. It corresponds to a minor version bump in semantic versioning. Fix is a bug fix, a patch version bump. Docs is documentation. Style is formatting with no logic change. Refactor is restructuring without adding features or fixing bugs. Test is test additions. Chore is maintenance work. Dependency updates, CI configuration. Perf is a performance improvement. A breaking change footer in the commit body signals a major version bump. Click. Look at the examples on the right. Each one is immediately informative without reading the diff. Feat, auth, add OAuth 2 login support, self-explanatory. Refactor, remove deprecated login endpoint. After the type is shorthand for a breaking change. Fix API, handle null response from users. You know exactly where to look and what was fixed. When every commit message follows this format, you can auto-generate changelogs with tools like conventional changelog, auto-bump versions, and filter by type in Git log. It turns your commit history into a first-class project artifact. Git hooks are shell scripts that run automatically at specific points in your Git workflow. They live in the .git/hooks/ directory and are not committed to the repository by default, which is why tools like pre-commit exist, so you can version the hook configuration. Click. The flowchart shows the lifecycle for a Git commit followed by a Git push. When you run Git commit, the pre-commit hook fires first. This is the ideal place to run your linter, formatter, and type checker. If the hook exits with code 0, success, Git proceeds. If it exits with anything else, the commit is aborted. You fix the issue and try again. Then the commit MSG hook runs to validate the message format, for example, enforcing conventional commit structure. Same logic, exit 0 to continue, non-zero to abort. When you Git push, the pre-push hook runs your test suite. This is your last line of defense before code reaches the remote. Click. Rather than writing these hooks by hand, the pre-commit framework handles everything. You write a .precommit-config.yaml that lists the hooks from community repos, formatters like Black, linters like Flake8, and hundreds of others. Pre-commit install installs the hooks. Pre-commit run, all files runs them manually. The beauty of this is that the configuration file is committed to the repository, so every developer on the team gets the same hooks automatically. Let's tie everything together by looking at exactly what happens inside Git when you run git commit-m init on a project with 2 files. Click. The diagram traces the object creation process. First, Git creates a blob object for each file. The blob for hello.py contains nothing but the raw file contents, hashed to produce its SHA-1 identifier A1B2C3. Same for readme.md, blob D4E5F6. If you had 10 copies of the same file across your project, they would all share one blob. Then Git creates a tree object. The tree maps file names to blob hashes. Blob A1B2C3 is called hello.py. Blob D4E5F6 is called readme.md. The tree represents your project's root directory as it exists in this commit. Its hash is G7H8I9. Then Git creates the commit object. It records tree G7H8I9, author Alice, date, and message. If this is not the first commit, it also records the parent commit's hash. The commit's hash is J1K2L3. Finally, Git updates the branch reference the file refs/head/main to point to J1K2L3. That is the entire pointer bump that makes commits work. Click. You can inspect all of this yourself with git cat file. Thead tells you the type of the object head points to. Thead prints its contents. Git ls tree head lists the tree entries. This mental model, blobs, trees, commits, refs, explains every Git behavior you will ever encounter. Here is a bird's eye view of the Git command landscape as a mind map, organized by category. Setup, init, clone, config. The once per project or once per machine commands. Snapshot, status, add, commit, Diff, the daily workflow. Branch, branch, switch, merge, rebase, the collaboration commands. Remote, remote, fetch, pull, push, talking to the outside world. Undo, restore, reset, revert, stash, your safety net commands. Inspect, log, show, blame, bisect, reflog. Investigation and archaeology. Tags, tag, and push tags for releases. If you are ever unsure which command to use, git help lists them all, and git less than command greater than help opens the full manual for any specific command. The Git documentation is genuinely excellent. Let's bring it all together. Core concepts. Git is a distributed version control system. Every clone is a full backup. Your project lives in 3 areas: working directory, staging area, and repository. Everything Git stores is a SHA-1 hashed object, blob, tree, commit, or tag. Head tracks exactly where you are in history. And branches are not copies. They are cheap, lightweight pointers. Key operations. The everyday loop is git add, git commit, git push. Merge preserves history. Rebase linearizes it. Stash is your work-in-progress clipboard. Reflog is your ultimate safety net for anything that seems lost. Best practices. Commit early and often, with meaningful, structured messages. Follow conventional commits so your history is parsable by both humans and tools. Never force push to shared branches. Maintain a comprehensive git ignore, especially protecting secrets. Always review git diff, staged before committing. Use feature branches and pull requests for any teamwork. And absolutely never commit API keys, passwords, or tokens, ever. Tools to explore from here. GitHub, GitLab, and Bitbucket for remote hosting and CI. The pre-commit framework for automated quality checks. GitCrypt for encrypting sensitive files committed to a repo. And Tig, a beautiful terminal UI for browsing Git history. That's a wrap on Git. We covered everything from how Git stores objects internally, all the way to professional workflows and advanced tools used in real engineering teams. The diagram on screen says it best. You learn, you practice, you push, you grow, and the cycle repeats. The only way to truly internalize Git is to use it. Use it on real projects. Break things on purpose. Use the reflog to recover them. That is how the concepts become muscle memory. Links in the description. The official Git documentation at git-scm.com is comprehensive and readable. LearnGitBranching.js.org is an interactive browser-based game that visualizes branches as you manipulate them. Excellent for solidifying the mental models. And ohshitgit.com is what you open when something has gone wrong and you need the plain English fix, fast. Thanks for watching, and keep shipping.